Okay, first it's important to recognize that every solution has two parts. It has what's called a solute and a solvent. Okay, now the solute is usually some kind of solid material that we're trying to break apart. Okay, it doesn't turn into a liquid, but it breaks apart into separate little particles, and sometimes we can't see those particles, but it's still there in the solution. The solvent is typically water, but it could be alcohol or some other sort of thing that will do the breaking down. Okay, so in most cases in chemistry, especially at this level, water is going to be our major solvent. Okay, so solvent does the breaking apart. Solute is the stuff that gets broken apart. Okay, now what we're going to do is we're going to work today with what's called molarity. It's a unit of concentration that's used in chemistry quite a bit, and it's defined as moles per liter. Now the reason this is important is if I have several solutions sitting on a shelf, they may all kind of look the same, like sort of clear, like there's really nothing in there, but one of them might have a lot of this sodium phosphate in it, and another one might have just a tiny bit. We call that a dilute solution. So what we have is a number that kind of tells us how much stuff is really dissolved in there. Okay, and there's lots of units for concentration. Percent by volume is a real common one, but in chemistry, molarity is one we use frequently. So what I'm going to do is make up an amount and just kind of show you the mechanics of how to calculate this and deal with it. I'm going to say, what if we had about 30 grams of sodium phosphate and we dissolved it in enough water to make a volume of 1,200 milliliters. Okay, now think about this for a minute. If I were to put just 1,200 milliliters of water into this container, and then I added 30 grams of sodium phosphate, well, that's going to push the volume up just a little bit above 1,200. But for all practical purposes right now, I'm just going to say that we're using about 1,200 milliliters of water, and we're going to get an approximate concentration. Okay, so we're going to use about 1,200 milliliters of water and put in 30 grams of sodium phosphate and dissolve it. Now what you want to really pay special attention to is units. Okay, units are really important. We need to have liters in terms of our measurement of volume to interpret this correctly. And over here, I see milliliters. So I'm immediately going to do what I've done many times. I'm going to change that to 1.2 liters. Okay, and I don't want to deal with 1,200 milliliters anymore. I'm going to stick with the liters. Okay, so this is what I'm going to work with. Now, I'll take a look at the solute. The moles, okay, well I don't have moles, I have grams. And the reason I have grams is when we go into a lab, you don't just measure out moles. Okay, you have to use the periodic table to do some converting. You measure out how much it weighs, but you can't really just go in and measure the moles of something. So we need we have 30 grams of sodium phosphate. We need to figure out how many moles that is. And you guys have done this many times, so I'm just going to remind you of it. We're going to take 30 grams sodium phosphate, Na3PO4, okay? And instead of having grams, we're going to convert it to moles. Okay, now this will look familiar to my students who've done this hundreds of times. I want grams to disappear, so grams goes on the bottom. Okay, and that's going to cancel it out, and I'll be left with moles on top. I know when I look at the periodic table, it shows me 1 mole of everything, but what I need to figure out is what it weighs. Okay, so the molar mass in the periodic table is its atomic mass. If I look up sodium, it's 23, and there's 3 of those. If I look up phosphorus, it's about 31, and oxygen is 16, but I have 4 of those. Now, I know those aren't exact masses, but we're getting an approximate measurement here anyway, so I'm just going to round them to the nearest whole number. So if I add all those up, I get 164 grams for every 1 mole. Well, I'm not putting 164 grams into this container. I'm only putting 30 in there, so I have a lot less than 1 mole. So what I need to do, remember this is like a big fraction. I multiply the numbers on top and I divide by the numbers on the bottom. I'm going to basically take 30 divided by 164 because a 1 doesn't really affect it. So I take 30 divided by 164, and when I do that, I'm going to get 0.183, and that's a rounded approximate number. Okay, but that right there is not the concentration, that's just the moles. Okay, and that happens to be the moles of this right here, the moles of sodium phosphate. Okay, so that's only part of the equation. Now I also have to deal with how much volume is in that solution. So to get molarity, I'm going to always take moles divided by liters. I take 0.183 moles divided by 1.2 liters. And when I do that, I'm going to get an amount that after I round it off is about 0.15 moles per liter. Okay, but instead of writing moles per liter, I'm just going to write a capital M. And when you see a capital M in chemistry, that's what it's referring to. it really means two different things: moles per liter, not just an amount of something that is in a single measurement. It's a ratio. Okay? Now that's how you calculate a molarity from scratch. What I want to show you now is how do I deal with a molarity if I see it and interpret it in light of something else. So I have a different problem. Okay, this is calculating molarity from scratch. Now let's take a look at how this one is the same type of information but slightly different. Okay, this says we wish to make 250 milliliters of a 0.05 capital M, so that's molarity right there, a 0.05 molar solution of potassium sulfate. So this is a situation where we're trying to mix a particular concentration. We have a target we're looking for, and this right here is the target. And here's the overall volume we have to have. Okay, but when we go in the lab, we need to know how many grams, like physically on a scale, how many grams to weigh out of potassium sulfate. So we're always going to start basically in the same spot. We're going to start with capital M equals moles over liters. And usually, out of these three things, you have two of them you can figure out. Okay, so in this case, I look what I have to work with, and I have a capital M right here. So I know the target molarity. I know the target concentration. That's going to go in right here. I also have a volume that I'm trying to achieve, and that's going to go in down here where liters is. And I'm going to set up a very simple proportion here. I have 0.05, that's my capital M, equals moles, which I don't know, over liters. And in this case, be careful, we don't milliliters. It's 0.25 liters. Always look for those units. Don't just grab a number. Okay. Now I need to solve this for moles. So to do that, we've done this before. We did this a whole lot with gas laws. We're going to turn this into a fraction over 1 so that we can cross multiply. So if I cross multiply, I get 1 times moles equals 0.05. Okay, we take these two things multiplied times 0.25. And I know I didn't write any units with some of these. We're going to interpret that in just a minute. But basically this one, I don't really need to, I can pretend it's not there. It doesn't really affect the math. So if I multiply these two together, it's going to tell me how many moles I need to have. So if I multiply those together, I get, see I did this right here, I get 0.0125 moles of potassium sulfate. Okay, so I just multiplied those together and gave me how many moles I had. Now be careful, watch out for the zeros here. If you get a lot of zeros, because things are very diluted, got to be real careful you're using the right amount. Now if I go into the lab, I can't measure out 0.0125 moles. There's no balance that's going to tell me that. I need to go use the periodic table. So we go back to our periodic table, we do a little conversion here. 0.0125 moles of K2SO4, get your units, your formula correct. I'm going to turn that into grams this time. Okay, I want moles to cancel out, so I'm going to put that on the bottom. Now, I look at the periodic table that always shows me 1 mole of everything. Okay, and I'm going to add up potassium, sulfur, and oxygen. I've got 2 potassiums, and each one weighs 39 grams per mole. So 39 times 2. 1 sulfur weighs 32 grams, and 4 oxygens weigh 16 times 4. I put all those together, I get 174 grams. So potassium sulfate's 174 grams per 1 mole, but I don't need 1 mole for this small solution I'm making. I only need that much. So I'm going to multiply the two things on top, divide by the one on the bottom, which doesn't really change it. So I'm really just multiplying the numbers on top. And when I do, I get an answer of 2.175. And now that represents grams of potassium sulfate. Those are the units that are left. What I've done is I kind of went in reverse. The previous problem we were trying to calculate a molarity. Here we had a target molarity we were trying to achieve. We had a certain volume we're trying to make, and we kind of went the other direction to figure out how many grams it would take for that to happen. Okay? One process is kind of the reverse of the other. They're both using the same formula. Always come back to this. Always start right there.